Let's take the time to quickly review some of the basics of complex numbers, right? So where do complex numbers come from? Well, let's say you're looking in just the reals here. And if you're looking in just the reals, you can consider polynomials with coefficients whose entries are real, right? So say x squared, you could look at like, well, really, it's a field here, but you could look at like r of x or even z of x. These are polynomials with integer coefficients, right? If you'd like to see this as a set, z, you say z adjoin x here. This is the set p of x polynomials. And let's say we could write this p of x as a naught plus a1 x plus et cetera, plus a in x to the n, and such that ai is an integer for all I, right? And solutions or roots of polynomials, we know roots of polynomials are where p of x equals 0. And you may ask yourself to solve like a naught plus a1x plus a2x squared plus et cetera, plus an x to the n. You may ask yourself, when is this equal to 0, right? And there are going to be n solutions. But what will turn out is that the real numbers are not a big enough field to contain all roots of a given polynomial, even one with purely integer coefficients. For example, if you were to look at just what are the roots of x squared plus 1 equals 0, right? Well, then the answer, the roots would be x squared equals -1. This answer, the root here, there's two roots because it's a quadratic, right? So the roots here are not in the reals. And so we need to expand our understanding here. We need to expand the field that we're taking numbers from. And the solution here, we know, says a solution of I, right, where x equals plus or minus I, those are the two roots here, where by definition I squared is equal to -1, or maybe more familiar, we're more used to seeing root -1, right? Let's say I equals root -1. This is our like unit imaginary number here, I, which is root -1. And what we need is that this belongs to the complex numbers, right? This isn't in the reals, this belongs to the complex numbers. And we denote the complex numbers with the Blackboard C here. So let's take a look at the complex numbers as a set algebraically, and also some of the geometry that's going on here. So as a set, C is defined to be those points Z, which equal A plus BI, such that A and B are real numbers here. So you can think about there being a one-to-one correspondence or a bijection or an isomorphism, right? Maybe I should have also said, if you have a surjection, this is an aside, a surjection plus an injection. This is also known as a bijection. In this specific context, we were calling them an isomorphism. Okay, but we also call them bijections. Anyway, there's a bijection here between the numbers Z equals A plus BI and ordered pairs AB, where A and B are in the reals. And because of that, we get an isomorphism between the complex numbers and R2, right? Namely one that sends the ordered pair AB to A plus BI. So let's look at the complex numbers as living in the plane, right? We'll just identify the complex numbers with R2 here, where the ordered pair AB is the same as saying A plus BI in this context, right? And so instead of now an X and Y coordinate, what we have is the real part of Z and we have the imaginary part of Z. And this language comes from writing Z as the real part of Z plus the imaginary part of Z times I, right? Excuse me. This basically acts as our X and Y here, but we don't really say X and Y in the complex setting, right? We kind of have, we think about the real component and the imaginary component. So if the complex numbers can be identified with R2 in such a way, I mean, the structure of the complex numbers is very different, as we'll see. Addition behaves differently, the product behaves differently, inverses behave differently, right? So like the algebraic structure that's going on here is much different, but just purely as a geometric object, you can think about these things as being the same thing, right? Because, well, every point can be described either as an ordered pair of real numbers or as a complex number, A plus BI. So let's look at addition in the complex plane. So here, what do we have? Well, you would take the sum of two complex numbers. So let's say we're taking like Z plus W here. This would be something like A plus BI plus C plus DI, right? If we gave those, if we wrote explicitly what Z and W were. And then we add component-wise. And what I mean by component-wise is you always add real parts and you always add imaginary parts. So this would simplify to A plus C plus B plus D times I, right? You're still combining like terms, even though even though we're in like the complex setting now, right? You're still just combining like terms. So let's look at like a very quick example here. Let's say we were looking at 3 plus 5i, and then we were adding this to 8 plus 2i. Well, what would the result be, right? This would be 11 plus 7i, because you add the real part together, and then you add the imaginary part together. And the real part plus the imaginary part is a complex number, right? What are some properties here? Let's look at a theorem. These are properties of addition in the complex plane, or in the complex numbers, right? Let's let Z, W, and V be complex numbers. Then we have the following properties. We have the complex addition as commutative, meaning Z plus W is W plus Z. This is commutativity. And I would like you guys to prove this stuff. This is really pretty standard stuff. I think it's very good for you to be able to prove. And you can prove this by, you know, give Z and W explicit names. Like if you say Z is A plus BI and W is C plus DI, well, show this property, right? What else do we have? We have the existence of an additive identity, meaning Z plus 0 is 0 plus Z. Well, that's just restating the commutativity. This is just Z, right? This is the additive identity. We also have the existence of an additive inverse, and that's Z plus -1 times Z, right? This is 0. This is the additive inverse. what else do we have? We have the associativity condition of complex addition, which means if you take z plus w first and then add v, well, that's the same as taking z plus first adding w plus v here. And this is associativity, right? And so we have these properties as well. And these are all pretty straightforward to prove, and I'd like to challenge you to prove these yourself. We also have multiplication of two complex numbers. So let's look at the multiplication in C here, right? Well, what does it mean if we take the product ZW? Well, that means we're taking A plus BI times C plus DI, right? So if this is the case, then we FOIL this, right? We treat this as first, outside, inside, last, right? Foiling, if you've heard that phrase before. So the first term is A times C, and then plus A times DI plus B times CI, and then the last term would be plus BDI squared, right? But we know I squared is defined to be -1, and so the real part of this product is AC minus BD. And then plus, it looks like we'll have AD plus BCI for the imaginary part of this. And so the product of two complex numbers is defined as follows here, but really you would just FOIL each time, right? So let's see a quick example of multiplication of two complex numbers. Let's say we take 2 minus I times 1 plus 3I. Right, well, that's 2 times 1, and then plus 6I minus I minus 3I squared, which is 2 plus 5I, and then that's -3, I squared is -1, right? So that'd be plus 3, so this will be 5 plus 5I, and that would be the product of an example of the product of these two complex numbers here. Let's look at some properties of the product of two complex numbers. So here's theorem, properties of complex multiplication. Okay. We have, and again, I would challenge you to prove these yourself. We have the complex multiplication is commutative, meaning ZW is WZ, right? This is commutativity. We have the associativity of complex multiplication. So if we took the product ZW times V, that's the same as Z times the product WV. This is associativity. We have the distributive property that if you take Z times W plus V, that's the same as ZW plus ZV. It's the distributive property. We have the multiplicative identity given by 1, right? Like the real number 1 is still the multiplicative identity here. 1Z equals Z. This is a multiplicative identity. And we also have the multiplicative inverse, which means for all complex non-zero numbers, there exists Z inverse, which we're really thinking of as 1 over Z, such that Z times Z inverse equals 1. But computing the inverse, right, it's 1 over Z, but we'll see how to actually compute the inverse of a complex number, because it's convention that we never leave imaginary numbers in the denominator. Okay, so we have these properties of multiplication of two complex numbers. We also have the notion of a complex conjugate. So let's give a definition here. Let's say Z equals A plus BI is some complex number. Then the complex conjugate of, let's say, of Z is, and it's defined to be Z bar equals A minus BI. So really you just flip the, right, Z bar, the conjugate, is the real part of z minus the imaginary part of zi. Right? You just flip the sign of the imaginary part, and that gives you the conjugate. So, I mean, let's look at some examples here. That's pretty straightforward, but still, if z is 3 plus 4i, then z bar is 3 minus 4i. If you had something purely imaginary, like I bar, right? Well, that's just negative I, because you're always flipping the sign of the imaginary part. So if we had something purely real, say like 7, well, conjugate of 7 is just 7, right? Because there's no imaginary part to flip here. And one thing you may notice here is if I were to take z bar bar, then this would be 3 plus 4i again, like back in the first example. And we'll see this property, and I'm kind of spoiling it, but you may notice, and it's not a mistake, that z is equal to z conjugate. Well, I mean, pretty straightforward proof, right? You just flip the sign of the imaginary part twice and you get back to where you started. Okay. So why do we care about the conjugate? Well, one reason we care is, let's look at the following claim. I claim that z times z conjugate is equal to a squared plus b squared, which is in the reals, right? If we have a, or like for z equals a plus bi here, right? And we'll see more why this is important, but for now, let's just build this understanding that if you take z times its conjugate, you get a real number, right? That's kind of what we want out of this. So here's the proof. Let's take z times z conjugate. Well, that's a plus bi times a minus bi, which is a squared, and then minus abi plus abi minus b squared I squared, which is a squared plus b squared, right? So pretty straightforward proof, just computing the product of a complex number with its conjugate. And we see we get a real number. Why do we care about that? Well, the reason we care about that is because this gives us a way of getting complex numbers out of the denominator, right? So here's kind of a note or a remark. It is standard to never leave complex, or let's say leave i's in the denominator. Of a complex number. So how do we get i's out of the denominator? To move i's to the numerator, we multiply the denominator by its complex conjugate. Okay, so let's see what we mean. If we have, for example, and this is an example that would also show the division of two complex numbers, right? So we have 2 minus I over 3 plus 4i. And we want to simplify this to a number of the form a plus bi, right? How do we do that? Because that's how complex numbers are written. They're written as a plus bi. So how do we figure out the division of two complex numbers in this form, right? Well, what we do is we always multiply the top and bottom by the conjugate of the denominator. So in this case, that's 3 minus 4i. And if we do this, well, then we have complex multiplication to compute in the numerator and the denominator, right? It looks like we're going to get 6 minus 8i minus 3i, and then it's going to be plus 4i squared. So that's minus 4 because I squared is -1. And we could simplify the top there. It's going to be 2 minus 11i. So let's go ahead and do that. Right? And then in the bottom, we know that the product of a complex number times its conjugate is just a squared plus b squared. So that's 3 squared plus 4 squared, which is going to be 9 plus 16, which is 25. Which means our complex number is 2 over 25 minus 11 over 25 with the I in the numerator, right? So this is not only an example of showing you how to get the complex number out of the denominator, but it's also showing you what the division of two complex numbers looks like. So let's look at some properties of the conjugate here. So here's a theorem, properties of complex conjugation. Cool. Well, we have that if you have z plus or minus w complex numbers, and you take the conjugate of the sum or difference, that's the same as first computing the conjugate term-wise, not a vector, just a conjugate. Right? So you can either compute the sum first and then take the conjugate of the sum, or you can compute the conjugate of each number and then take the sum or difference of the conjugates, and those are the same thing. We also have that property for the product. So you can either take the conjugate of the product, or you can take the product of the conjugates, right? So these first two lines are saying the sum of the conjugates is the conjugate of the sum, and the second line says the conjugate of the product is the product of the conjugates. We have one that we've kind of spoiled already, is that if you take the conjugate of a conjugate, you get the complex number back. We also have that if you take the conjugate of a fraction, that's the fraction of the conjugates. So z over w conjugate is z conjugate over w conjugate. And then the last one we have is that z is a real number if and only if its conjugate is itself, right? And that's because that comes from not having an imaginary part to flip the sign of, right? So now that we have some examples and properties of the conjugate, let's define the multiplicative inverse of a complex number. This is the multiplicative inverse. Okay. So let's let z be a plus bi. Then z inverse is defined to be 1 over a plus bi, right? We're looking at z inverse as being 1 over z. And so for obvious reasons, we're considering non-zero elements of the complex numbers here, right? Well, we always get the complex number out of the denominator. So we can simplify this to a minus bi over a plus bi times a minus bi, because we multiply the top and bottom by the complex conjugate of the denominator. And you can see relatively quickly that this simplifies to a over a squared plus b squared for the real part minus b over a squared plus b squared for the imaginary part. And so this is our z inverse here. This is how we would define the inverse element of a complex number. Okay. The last thing I want to look at for this video, and then I think I'll make maybe a very short second video on complex numbers, is we'll spend the time to look at the polar form of a complex number. But for now, let's just give a quick definition here. The modulus, which is really complex absolute value, if you would like to think complex absolute value, right? The modulus of a complex number z equals a plus bi is, and we write this as absolute value of z. It's equal to root a squared plus b squared. And you may notice this value is, i.e., modulus of z is root z times z conjugate. This is another way of looking at the modulus. And we'll see what this is doing for us when we start to look at the polar form of complex numbers. There's a much better geometric understanding of the modulus of a complex number in the context of complex numbers expressed in their polar form, right? And so that's where we'll go from here.